Let's explore the spanning tree protocol, also known as STP, a crucial mechanism for loop prevention in switch networks. This presentation will guide you through the fundamentals of STP, explaining how it works and why it's essential for maintaining a stable network environment. In the illustration, you can see a typical network topology with multiple switches connected in a way that could potentially create loops. Network loops can cause severe problems. First is broadcast storms, which involves the endless multiplication of broadcast frames, overwhelming the network. Then there is MAC address table instability, which is caused by constant changes in switch tables, which leads to confusion and inefficient forwarding. After this, multiple frame transmission occurs where duplicate frames can reach the destination, causing processing overhead. Lastly, network performance degradation takes place due to high CPU usage and bandwidth consumption on the network. Spanning tree protocol is an IEEE 802.1d standard designed to prevent loops in switched networks while maintaining network redundancy. It creates a loop-free logical topology by selectively blocking redundant links, ensuring only one active path between any two network nodes. STP automatically prevents switching loops at layer 2, maintains backup paths for redundancy, dynamically responds to topology changes, operates transparently to end devices, and it is a standardized protocol supported by all switches. Let's familiarize ourselves with some key STP terminologies. First is the root bridge. This is the switch with the lowest bridge ID that serves as the central reference point for the spanning tree. Then we have bridge ID. It is the combination of a priority value, which is 2 bytes, and a MAC address, which is 6 bytes, that uniquely identifies each switch. Also, there are port states such as blocking, listening, learning, forwarding, and disabled states that control frame forwarding. And lastly, port roles are root port, designated port, and non-designated, also known as blocked port. Let's delve deeper into STP port roles and states. The root port is the port on a non-root bridge that provides the best path to the root bridge. Each non-root switch has exactly one root port. The designated port is the port on each segment responsible for forwarding frames toward the root bridge. All ports on the root bridge are designated ports. A non-designated port refers to the ports that are neither root nor designated ports. These ports are placed in blocking state to prevent loops. The port states are blocking, listening, learning, forwarding, and disabled. Transitioning through these states takes time, with convergence taking around 50 seconds. STP operation involves a few key steps. Firstly, switches exchange bridge protocol data units, also known as BPDUs, to elect the switch with the lowest bridge ID as the root bridge. Secondly, each non-root switch identifies its best path to the root bridge and designates that port as the root port. Thirdly, for each network segment, the switch with the best path to the root becomes the designated switch, and its port is the designated port. Lastly, all ports that are neither root ports nor designated ports are placed in the blocking state to prevent loops. A bridge protocol data unit contains header fields, protocol information, and bridge information. There are several variations of the spanning tree protocol. First is the IEEE 802.1d STP, the original standard with approximately 50-second convergence time. It uses a single spanning tree for the entire network. Rapid STP is also known as 802.1w. It has faster convergence, about 1 to 2 seconds with backward compatibility, and it introduces new port states and roles. Multiple STP is 802.1s. It allows multiple spanning trees for different virtual LANs, also known as VLANs, enabling load balancing across redundant links. Per VLAN spanning tree is a Cisco proprietary protocol that runs a separate STP instance for each VLAN. Rapid PVST Plus is the faster version. Basic STP configuration involves enabling STP, setting bridge priority, and configuring port costs and priority. You can verify STP configuration using show commands. STP also has several enhancements and security features. PortFast allows access ports to bypass listening and learning states, moving directly to the forwarding state, and it should only be used for end-device connections. BPDU Guard disables a PortFast-enabled port if it receives a BPDU. This protects against unauthorized switch connections. Root Guard prevents external switches from becoming the root bridge by blocking ports that receive superior BPDUs. Loop Guard prevents loops caused by unidirectional link failures by disabling ports that stop receiving BPDUs. Configuring these enhancements involves specific commands on the switch. Here are some best practices to keep in mind. Plan root bridge placement. Manually configure the root bridge in the center of your network topology for optimal traffic flow. Implement STP security features. Use BPDU Guard on access ports, Root Guard on distribution to access links, and Loop Guard on critical links. Use rapid STP variants. Implement RSTP or rapid PVST+ for faster convergence times in enterprise networks. Configure load balancing. Use MSTP or PVST+ to distribute traffic across multiple links by configuring different root bridges for different VLANs. In summary, STP prevents Layer 2 loops while maintaining network redundancy. It creates a loop-free logical topology by selectively blocking redundant links. Modern variants like RSTP provide faster convergence times. STP enhancements like PortFast and BPDU Guard improve security and performance. Proper STP design is critical for network stability and optimal performance. Finally, STP is a fundamental protocol that all network engineers must understand. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.